Thanks for joining. My name's Rob Morlino. I'm the host here, I guess. I work at the University of Pittsburgh as the Executive Director of Communications and Marketing at the Pitt Clinical and Translational Science Institute. I would like to, and it is my pleasure, to introduce today's speaker, Sham Visweswaran, um, to lead our talk today. Dr. Visweswaran is a professor in the Department of Biomedical Informatics and Intelligent Systems program at the University of Pittsburgh. His research sits at the intersection of artificial intelligence and clinical care, spanning AI-based clinical decision support, patient-specific modeling for precision medicine, causal discovery for biomedical data, and research data warehousing. Today's topic gets at one of the most practical questions in modern translational research, I think, which is what can we do with the data we have already, and in this case, within the ENACT network. So the ENACT network now connects more than 140 million patient records across CTSA hubs, and aggregated counts are often the first and I would say the most common view that researchers get into that data. So, Dr. Visweswaran's talk, Unlocking the Potential of Aggregated Counts from the ENACT Network, will explore how to turn those counts into something more, how to leverage them into something, even more useful. Faster cohort discovery, sharper feasibility assessments, and new research questions that maybe we couldn't ask before. So please welcome me in. Please join me in welcoming Dr. Sham Visweswaran.
Okay. Thank you, Rob, for that introduction. So as Rob mentioned, I'm going to talk about aggregated counts and how this can be used for a variety of reasons from the ENACT network. And this is sort of going back to the start of the ENACT network when it started out as the ACT network, where the original goal was to really set it up to provide aggregated counts. And I will talk a little bit about the history, and then we'll get into some of the more recent uses of these counts for research purposes. Okay, this slide is just to tell you that we hold this grand rounds monthly. We cover a wide range of topics related to real-world evidence. And we have covered a bunch of interesting topics in the past, and today we'll be talking about the aggregated counts. So just to give you an overview of this session, a little bit of introduction, and then which Rob has already done. And we'll hop straight into the presentation. I hope to leave a fair amount of time towards the end for question and answers. And then we'll just tell you when the next monthly grand rounds will be. And as we go along, you are free to enter your questions in the Zoom chat, or you can hold them off till the very end. So as Rob mentioned, so I'm here, the professor and interim chair of biomedical informatics, also one of the MPIs of the ENACT network, and I've been involved in the ENACT network since its beginnings when it was called the ACT network. So the objectives are fairly straightforward. How do we use this aggregated counts from ENACT? A little bit of interpretation, what do we mean by these counts? And I will give you a list, which is not a comprehensive list by any shot, about the kinds of studies that can be done using just patient counts. And then I'll give you two quite recent examples of specific studies that we have done here from Pittsburgh using aggregated counts. So just to set the stage, which I think a lot of you already know about ENACT, it's a federated network, which means the data reside at the local institutions. And there are now two ways to get this data. One is the traditional way, the way the ACT network was originally set up, which is there is a query tool called the Shrine tool through which you can run queries, and what you get back is just aggregated counts. And more recently, we have started building out the ENACT enclaves, where you can request line level data for certain cohorts for a research study, and then they get moved into that central place where you can do deeper analytics. But today we're going to talk how to do research with just counts. And just to give you a little bit of how the technology is set up, the Shrine network, which includes the Shrine hub, which sits in Harvard, which is what connects all the queries which run through Shrine to the local data repositories and then brings back the results, is now interoperable. It's been interoperable for a while. So, which means that the local sites can either have an I2B2 data repository with the data in it, or they can have an OMOP data repository. And as long as they use the ENACT ontology, the entire network interoperates. And as users who are running queries through Shrine, you're agnostic to what the underlying database is at a local institution, whether it's an I2B2 or an OMOP, which is sort of a very nice step for this network, because we know that many of the other projects which use reuse data for EHR are usually stuck to like one data model, while here we have now two data models which can interoperate. And this just gives you a screenshot of the modern Shrine interface. Essentially, this is what you use to construct queries, which will then enable the local data repositories to respond by passing counts back. So on one side, you have the ontology, which is laid out, and concepts and terms which are there in the ontology can be dragged and dropped onto these various panels, and you can create fairly complex queries. So the kinds of queries that you can create in Shrine, fundamentally, it uses Boolean logic. So you can AND concepts by dropping concepts in two different panels. So for example, if you wanted patients who have both diabetes and are taking insulin, you would drop these two concepts in two different panels, and then you'd get patients who satisfy both these conditions. You can also OR conditions by putting in concepts in the same panel. So if you drag and drop diabetes and insulin into a single panel, then they get ORed, and you get patients who either have diabetes or insulin. And finally, you can also have the exclusion criteria, the NOT criteria. So you could drop in something like diabetes into a panel and attach the NOT criterion, and you'd get back patients who don't have diabetes. This is kind of standard Boolean logic, which is the key way to construct queries in Shrine. But on top of that, there are additional constraints which can be applied to these queries. And two very useful ones are date range. That means you can limit events to a specified time period. So you can limit, for example, patients who have a diagnosis of diabetes attached to them for the year 2025. And you just get patients of that, which satisfy that criteria back. There are also numeric constraints. This is especially useful for lab values. So you can construct a query which says, give me patients who have, say, for example, hemoglobin greater than 6, hemoglobin A1C greater than 6. And what Shrine gives back are aggregated counts. And what we mean by an aggregated count is the number of patients who satisfy that query. So the count is really counting the number of individuals or number of patients. And you can get no other type of counts through Shrine. This is the only kind that you can get. So for example, if you run a query and the Shrine executes this query, and as the counts come back, they populate the interface. And here you can see that here is a query which has been running for few minutes. And so some of the counts are come back and they get populated. And so when you see a count like, say 19,535 plus or minus 10 patients, it's always patients that you get back. And in this particular case, the query we are running is pretty straightforward. It's an ICD-10 code of Q99, which is just congenital malformations. And it's just bringing back how many people there are at each site who satisfy that particular criterion. So you get back patient counts per site. And you'll also notice that there is some rounding which happens, this obfuscation which is attached, which is plus minus 10 patients. So you don't get the exact count, but you get plus or minus 10 of that count. This is to preserve basically patient privacy. And I'll talk a little bit about how we have already gotten a new version of Shrine, which reduces this to plus minus 3, which is useful under certain conditions. So the question really is, we can run queries, which can be as simple as this, or it can be very, very complicated. And you're just going to get back counts from every site, which satisfy the query. And you can, of course, you're free to run a whole series of these queries. And how can you do this and still do some interesting research? So that's basically what the talk is about for today. So I'm just going to list a bunch of things that we can do with just counts, and then I'll give you more concrete examples of what we have done. The very first one is cohort estimation. And this is what this project was initially set up to do. And I'll talk a little bit about this in the next slide or so. But the idea here is that you have access to a large number of patient records or the patient EHRs, in this case, pretty much across the country from all these various CTSA sites. And from that, you're trying to estimate how many patients you have who might fulfill, say, the inclusion and exclusion criteria for a clinical trial. So that's sort of one big use case for this use of these counts. We can also do research, and I'll show you examples of this down the line, where we can just use these counts. Here are a couple of examples that fall under the research category. So you can do epidemiological kind of research, where you can estimate, say, the prevalence and incidence of a condition across geographical regions, because we get counts back from each site, and you know which site is returning it. Across demographics, because the ontology has got concepts for age and sex and race, and you can use that to slice and dice, as well as across time periods. So you can compare multiple time periods, and because Shrine allows you to attach time periods, you can do that too. And I'll give you an example of how we have done a particular disease, this epidemiology. We can also do pharmacoepidemiology. So we can estimate, for example, the prevalence and incidence of medication effectiveness or adverse effects, again, across geography, demographics, or time periods. And I'll show you an example of that too. Now, beyond that, you can also do surveillance. Surveillance, for example, syndromic surveillance, which is the mainstay of tracking epidemics or identifying new emerging diseases, where you can monitor, say, for example, medication patterns, ICD code patterns over time. You can also do pharmacovigilance, which is an extension of pharmacoepidemiology, which I showed you in the last slide, where we can follow up medications, especially which have been newly introduced in the market, and monitor them for side effects or even comparative effectiveness. And this is of great interest to the FDA, that they would like to do pharmacovigilance at scale. And in fact, they have had a network called the Sentinel, which does this in a somewhat different way, where it's not automated, but actually the queries get run manually at the participating sites, and counts are returned back to this FDA for the kinds of things that they are interested in. And finally, there's clinical evidence generation. What this means is that we can use EHR data to generate real-world evidence for clinical questions that are not addressed by guidelines and controlled trials. And this come up all the time if you ask physicians. And in fact, we have a pilot underway currently in the ENACT Network, which is actually doing this. And in a future talk, you'll hear in great detail about how we are doing clinical evidence generation. Here, I just want to point out, this is just done with counts by using the Shrine tool. And here are a couple of examples, like you can do treatment effectiveness, a new type of drug is on the market for a particular condition, and the physician wants to know how effective this new drug is, say, compared to the status quo. Or you can even evaluate care pathway outcomes. And by no means is this a comprehensive list of kinds of things that you can do with counts, but these are some of the key categories of things that you can do with counts. So let me just briefly talk about cohort estimation. And the reason I want to talk a little bit about this is that ENACT began as the ACT network, and ACT stands for Accrual of Patients to Clinical Trials. That was basically the original purpose when this was started almost about 10 years ago. And the reason was that inadequate patient recruitment is a leading cause of failure in NIH-funded clinical trials, and also other, even in non-NIH-funded clinical trials. And then the number is quite staggering. Up to 86% of all US clinical trials fail to recruit the required number of subjects on time. And so the goal of ACT was to use aggregated patient counts to estimate the availability of eligible research subjects even before you embark on a clinical trial. And this has been used to some extent by the RIC and the 10, which is CTSA entities charged with actually studying the feasibility of clinical trials and understanding how many patients are available given the inclusion-exclusion criteria. And we can still use it that way. And I think different sites use it that way to some extent. But about 5 years ago, ACT was funded as a separate grant. It evolved into the ENACT Network, which is the Evolve to Next Generation ACT Network. And as part of the grant, the focus now shifted to using the data for research beyond this cohort discovery purpose. And so that's what I'm going to talk about for the rest of my time here. So first, disease epidemiology. So I will talk about a particular use case, this postpartum hemorrhage that we looked into. A little bit of background on this. Postpartum hemorrhage, or PPH, is excessive blood loss during childbirth. PPH is a public health concern now because it's a leading cause of maternal mortality worldwide, and its incidence in the US has been increasing over the past 20, 25 years. And the reason that we know about this is that the AHRQ actually generates a report every 10 years, which looks into the incidence and prevalence of postpartum hemorrhage. And they do this because AHRQ collects 20% of data on 20% of all US inpatient hospitalized annually. This is called the National Inpatient Sample. And this is used to also study and characterize the incidence, risk factors, and comorbidities of postpartum hemorrhage. And this is a great use case for us because we can now actually use ENACT and take the results that we get from the ENACT network and compare ourselves to what HRQ does, which uses line level data to be able to do this. And so this provides a way to confirm that, yes, we don't have line level data, but we have counts, and we can still do a fair amount of characterization of PPH that AHRQ is able to do. So that was sort of the goal of this particular study. And so we evaluated the feasibility of using patient counts to estimate the incidence, risk factors, and comorbidities of PPH. And this is pretty much what AHRQ does every 10 years on PPH. These are the three things that they look at: incidence, risk factors, and comorbidities. And so this is what we did. So we pulled data from 8 ENACT sites. And the main reason why it's just 8 and not all of the sites on the network is that to do the study, we did the simplest possible thing, which is to only include sites which return counts for all the queries that we ran. And as you can imagine, there's a whole slew of queries that we run to be able to conduct this study. And we know that because of the technology, as well as the fact that sites go up and down, you're not going to get responses from every site every time. So it's an open statistical problem how you handle with missingness, which is both sort of systemic as well as random. And that is a very important area that we are looking into. But for this particular study, we took the easy way out and we said, we'll just take only the sites which return data for all the queries that we ran. And that was 8 sites. And it's a fairly big number that we get. We looked at the years 2005 to 2022, and we ran queries so that we got counts on an annual basis across this time period. So what we really use for the analysis is annual cross-sectional analysis. So the data itself that we get, the demographic characteristics, which are there in the ACT ontology, and every time you run a query, you can always get the demographics of your results. So that's easy. We looked at 7 risk factors and 8 maternal comorbidities. We picked these basically based on the AHRQ's reports. This is what they look at. The data itself consisted of women with hospitalized deliveries, which was about 700,000 in our case when we pooled the data from these 8 sites, of which about 56,000 had PPH and the rest did not have PPH. And our primary analysis was annual cross-sectional analysis being done for every year from 2005 to 2022. So this is the first thing we wanted to see. We wanted to see what's the incidence of PPH. And this is plotted as incidence per 100,000 deliveries. And as you can see, by the blue dots are the actual pooled counts that we get, and the dotted red line is a trend line which has been plotted, and it's going up steadily, and it's actually statistically significant with a p-value less than 0.05. And so around 2005, it's about 5,000 or so per 100,000 women. And then by 2022, it's reached about 6,500 or so. And the last HRQ report, which came out about 6 years ago, I think they do it like on the every 10th year, when we compared their incidence to ours, it tracks pretty closely to what the HRQ had in their last report. So we also looked at the PPH incidence on the whole during this time period, broken down by race, by risk factors and comorbidities. So race is in green, risk factors in blue, comorbidities in red. The y-axis is a little bit hard to read here, the labels. But basically, this is sorted in such a way that you have increasing rate of PPH in that particular group from top to bottom. So if you look at the green bars, the bottommost green bar has got the highest rate, and that's the Asian category. And that's actually something which is relatively new that we found. It seems that the Asian women's PPH rate is higher, and it's been going up at a pretty rapid clip, especially in the past decade or so, compared to the other categories, the race categories. Blue ones are the risk factors. The one at the bottom, which is kind of obvious, is severe eclampsia. So severe eclampsia often is complicated by difficult delivery, and PPH is often a component of it. And this is pretty much similar to what HRQ finds. And then among the comorbidities, the one with the highest PPH rate is operative vaginal deliveries, because anytime they operate to get the baby out, you tend to have, your chance of bleeding is higher. So any kind of bleeding counts, including operative bleeding for PPH. And that also tracks closely with what HRQ found. This plot is just to show you for the comorbidities. So there are these comorbidities, which are obesity, pre-gestational diabetes, gestational diabetes, asthma, chronic hypertension, antepartum hemorrhage, operative vaginal delivery in the past, primary cesarean section. These are standard comorbidities that the HRQ reports look at. And here what we have done is the blue bars tell you what the prevalence of that comorbidity is, given that the mother had a PPH. And the red one is what's the rate of PPH given a particular comorbidity, an orange bar. So the orange bar is somewhat easier to interpret because you just want to know which, for example, if you wanted to know among the comorbidities what has the highest PPH rate, you can just look at the orange bars, and if you look at the one which is the tallest, which is operative vaginal delivery, that has the highest prevalence of PPH. Now, if you invert it, and if you want to know among PPH mothers, what's the highest prevailing comorbidity, it turns to be cesarean section, because obviously there's more bleeding when they operate versus a natural delivery. So this was something we did additional, which the HRQ doesn't do. So that's just to give you a sense of that you can do to a certain extent epidemiology, and in fact even replicate what has been done with line level data. Now there are challenges to using the ENACT network, the way our technology is set up, and here are a few of them. One is the rounding of the data that happens with the counts, the data obfuscation problem. As long as you're looking at large counts, now you're fine. But once you get to smaller counts, because of this plus minus 10, you may not be able to make reliable estimates. So currently, what we do is we tend to only present results where we're using large counts, where the inference or the evidence is pretty strong. When you're looking at tens of thousands, plus or minus 10 doesn't impact much your estimates of whatever you're estimating, whether it's incidence or prevalence or things like that. The second one is a pretty interesting problem. Now, what we really care about with PPH in terms of epidemiology, and if you look at the denominators, let me go back. So if you look at this trend, which essentially is plotting the incidence of PPH, the denominator for this is essentially the number of deliveries. That's what standard epidemiology uses. But as I told you, the counts that we get back are counts of individuals, in this case, women who have delivered in the hospital. And there is no way for us to really get counts of number of deliveries. So in this particular case, let's say over a 20-year period, if you ran a query which says, give me the number of people who had deliveries, you're going to undercount the number of deliveries because on average, I think a woman has about 2 deliveries in the US. So we figured out a way to sort of mitigate this problem where we actually wanted to count the number of deliveries and not count the number of women. But given that we get only the count of women back, we did our best to approximate that count to what would be the count of deliveries. So all the counts, all the queries that we ran were fixed to a time period of 1 year. So the chances of basically someone having multiple deliveries within a year is somewhat smaller, much smaller than the chances of a woman having multiple deliveries over a 20-year period. So by restricting most of our queries, all of our queries to 1 year intervals, the counts that we get back, even though they're counts of women who are hospitalized for deliveries, it approximates quite well the number of deliveries itself. But just to be clear, in the paper, we still use the denominator as number of women who are hospitalized for deliveries, just to make it clear that that's actually what we're getting back, but we are pretty confident that it tracks closely to the number of deliveries, which is what is used in the field. And finally, the third problem is that we're relying on ICD-9 and 10 codes to define postpartum hemorrhage and deliveries and comorbidities and risk factors. And there are multiple ways to code some of the concepts that we are running or that we are using. Sometimes they might be coded with ICD codes, sometimes with CPT codes. So you can imagine that there are procedures done during delivery which are coded by CPT rather than ICD codes, or typically they're supposed to be coded with both. But there is site-to-site variability on how this is done. Now, the reason we used only ICD codes is because that's what the AHRQ uses. So we wanted to be closely tied to what the AHRQ did so that we can compare ourselves to them. But in the future, if we were to redo this, we would just include other kinds of codes which represent the concepts that we are using in these queries so that you have better computable phenotypes. This is just to show you, this is the team, and this particular paper has been accepted for publication in NPJ Health Systems, and it should be out in the next few weeks. I just want to point out that typically, to be able to do this kind of study, you kind of need 3 skill sets, which is represented in this team. You need somebody who has domain expertise in this area that you're studying. You need another person who understands the informatics, the technology that we're using, Shrine, how data is coded and mapped to ontologies, and what would be appropriate computable phenotypes. So that's the informatics skill set. And finally, you need a statistical background, biostatistical background, who comes up with the appropriate study design. And that's how the study was. All 3 were represented. And I'll now move on to the next one. So the next one is looking at pharmacovigilance. And this is a more newer study. And we were looking at basically anti-diabetic medications. So to give you a little bit background, this is getting to how do we monitor for safety of medications. Almost all the data that is obtained typically by the FDA, the safety of medications is either derived through clinical trials or through analysis of line level data. And this data could be claims data or EHR data, and that's what the Sentinel network does. And basically, we wanted to study how we can use ENACT as an alternative framework to be able to do timely large-scale analysis of medication safety while preserving patient privacy, and see whether we can do this. And so we looked at this particular issue of the fact that for diabetes, new classes of agents have been developed in the past 20 years. And the newest agent is sodium glucose cotransporter 2 inhibitors, the SGLT2I. And we wanted to compare the safety profile or the adverse effect profile of this newest class against two older classes of medications, which are the GLP-1RA and the DPP-4I. And this is kind of the stuff that FDA wants. This is the kind of stuff that even clinicians would want to know, is given that we have older classes of medications and newer classes of medications are usually more expensive. Is it the case that it's more effective? And is it the case that its side effect profile is different or its adverse effects are different? So that's kind of why we selected this this way. And this is set up very similar to the previous study. In this case, we again restricted ourselves only to the sites which return data for all the queries. In this case, there were 11 sites. We looked at data from 10 years, 1 decade, from 2012 to 2022. The demographic characteristics, which are there in the ACT ontology, and we looked at 12 adverse outcomes following medication initiation, as well as 23 pre-existing comorbidities for each medication class. And these are the kinds of things that have been done in the literature. So in this case, the counts that we have are somewhat similar for these three classes of agents, about 250,000 each from these 11 sites. And the primary analysis that we use here is the incidence rate ratio. In this case, it's actually adjusted using multivariate negative binomial regression, and the adjustment is for age, sex, race, and ethnicity. These are the typical things that is done to look at these rates. Typically, you would also adjust it to comorbidities, but with the way ENACT Network is set up, it's a little bit more complicated to do that. And so we didn't do that. So we did kind of the simpler version, which is adjusted to age, sex, race, and ethnicity. So I'll show you some of the results, which now we're putting together in the manuscript. So the first one was to compare one of the older classes, which is GLP-1RA, with this new class, the SGLT2I group. And you can see that we have a forest plot, which looks at these adverse effects. If the numbers are in red, that means that the new class, which is the SGL2 class, has a lower risk of that particular adverse effect compared to the older class. So you can see that there are two of these: hypotension, lower limb amputation, which are lower in the newer medications compared to the older class. And you can see that it's actually statistically significant because the 95% confidence interval that's indicated by that horizontal black line doesn't overlap that red vertical line. You can also see that pretty much all the other side effects are similar statistically to the older medication. And there isn't a side effect which is significantly higher in the new medication, because you don't see any of the green colored numbers. If you look at their confidence intervals, none of them, all of them cross the red vertical line. And that tells you that it's not statistically significant. So this establishes what's known to some extent in the literature, that SGL2 is superior for some of these side effects without any loss in the other side effects. So it's not inferior in any of the other side effects. And one particular thing of interest out here is that the lower limb amputation especially is of concern, because that's a big side effect or an adverse effect. And it's good to know that this new class of medication is significantly lower than the older class. Now, this is the comparison with the other older class, DPP4I. And in this case, it's even better. The profile of SGL2 is pretty superior to DPP. And there are several side effects that you can see are significantly lower. There's hypoglycemia, which is lower, acute kidney injury, acute pancreatitis, false or osteoporosis, hypotension, as well as severe mental health diagnosis. And 3 or 4 side effects which are in the green, actually none of them are significantly higher for SGL2. So this basically tells us that you can just use counts and you can get a large number of patients to do this kind of pharmacoepidemiology and establish this kind of side effect profiles with counts-based analysis by using appropriate statistical methods. So it's quite powerful that you can do this just with counts. So the challenges are similar to the previous study, small counts. So if you slice and dice the data, and in fact, we had a side effect or 2 which are quite rare. And so the counts become very small, and those are not included because they're just too small. And we just took only the side effects that have decent sized counts so that we can do the statistics. The other interesting part of this study is that here we are focused on medications. And medications, the way medications are captured in the EHR are at 3 levels. The commonest one is at the level of the medication order or the medication script. So whether you're in the inpatient or the outpatient, someone has to put this order in. And that is always there for a patient. That piece of data is always there that they were ordered this medication. But ordering a medication doesn't mean that the patient actually took the medication. There are a couple of steps which come after that. Because once the medication is ordered, it needs to be filled. So if it's an outpatient script, the patient has to go over to the pharmacy, get it filled. And if it's an inpatient, then after the order is put in, the central pharmacy has to fill in that order and send that medication down to the particular floor. And the best way to know that someone has taken a medication is the administration component, that the medication was actually administered. But that is captured only in a very small number of patients, typically in settings like the intensive care unit, where whoever is administering the medication will actually record it in the EHR. So one of the approximations that a pharmacoepi kind of study makes is that we're going to rely mostly on medication orders because that's what is really available in the EHR. And that's approximating the fact that the person is taking the medication. So you're probably overestimating the number of people who are actually taking this medication. So it would be nice to know or nice to figure out in the future whether there's a statistical way where someone has looked at all 3 levels in a data set and figured out how to adjust for taking medication orders, how to adjust it downwards to reflect the actual medication administration. But I guess if you're really dealing with large numbers, it may not be that big of a problem, assuming that the number of people who don't ever fill a medication, or they fill a medication and then they don't actually take it, is probably pretty small. But it's good to know that this is a limitation of using medication-based analysis. And again, the team which does this has got expertise in pharmacoepidemiology, informatics, and biostatistics. And there is a manuscript in preparation that is describing all these results. So those are sort of the 2 concrete studies that we have done from PIT. And so let me just list out a few of the advantages and limitations of using a network like this, which just returns patient counts. One big advantage of the ENACT is that because we have this umbrella IRB, you don't need an IRB for individual studies, especially if you're doing counts-based analysis. You have a user-friendly interface. You can do interactive querying, so you can keep refining the queries. You can run a lot of queries. And of course, you have access to a large number of sites and EHRs. Now, the limitations, one big limitation is the missingness issue. There is also the second limitation, the rounding problem. There's a third one, which is you really have to understand both how the data is captured and the study that you're conducting to come up with the most appropriate computable phenotypes. And it can be tricky at times. Like, for example, I pointed out that what we really care about in PPH or epidemiologists care about is the number of deliveries and not the number of women. And so we have to understand and have a fair amount of both informatics knowledge and clinical knowledge to say, okay, we can approximate it in this way by running the queries in such a way that the time periods are bound by 1 year. And the final limitation is that you're only getting one type of counts, it's patient counts. You don't get number of deliveries. You don't get number of scripts or prescriptions. What you get is number of patients. So we are in the process of introducing some new capabilities to address some of these challenges. So reducing the obfuscation, the rounding. The new Shrine now reduces this to ±3. And the technology working group worked on this. It's being rolled out. And this will enable to do these kind of studies where you're looking at maybe rare side effects or rare conditions where small counts are important. And if you have it down to ±3, it's definitely far better than using the ±10. The second one is coming up with appropriate computable phenotypes. One interesting approach to this, and the NLP working group is actually working on this in the context of clinical evidence generation, but can also be used for just doing any kind of research which involves generating computable phenotypes, is why not use an AI-based approach to help us build appropriate computable phenotypes? Because it does take a while. It takes a fair amount of effort to come up with appropriate computable phenotypes, and we iterate through these definitions once we understand the issues, and speeding that process up and enabling people who don't have such deep informatics expertise to be able to define these computable phenotypes and run these queries would be really helpful. The third one is automating Shrine queries. As you can imagine, these two studies took many hundreds of queries were run to be able to generate the counts that were used in the analysis. So it would be useful to have a tool that can automate queries, which can run queries on your behalf. And so we have a tool which is, we hope to build this out here at the PIT ENACT group. And finally, even automating analysis. It turns out that these analyses are really using only a handful of statistical quantities and estimates. And right now, when we do it manually, you have to pull down these results, put them in the spreadsheet, do some manual manipulation, and then feed them into, say, R code to do this analysis. And if you can automate this, it would cut down the errors as well as, again, speed up the process. So that's something also where we have developed a prototype, and I'll show you a little bit of that. Okay, I guess we have only about 10 minutes left, so I'll go through this a little bit quickly. So incidence rate ratio is something very common, whether you're looking at epidemiology of a condition or the side effect of, say, a medication. And it basically comes down to using 4 counts. And this is a tool which we have prototyped at this point, which has got a nice interface. And you can basically upload files that you get out of the Shrine interface into this tool. And it will basically be able to compute statistics like the incidence rate ratio, the 95% confidence interval, and the p-value. So that's one thing, which is sort of the base thing that we do for many of these studies, is the incidence rate and the incidence rate ratio. The other thing is it can do meta-analysis, random and fixed effect models, which is what we did with the diabetes medication, that we want to do a meta-analysis across all the sites data. So if once the data is in an Excel spreadsheet, and it's usually each row represents a site, now you can feed this kind of a file into this tool that we have developed, and it will plot out these forest plots for you. So here is one. On one side, it's a fixed effect model, and the other one is a random effect model. So you can pick the one you want, or you want both, you can get them. These are the two standard types of meta-analysis which is done with incidence rates. And this is the team again, which has been involved in building this out. So I think with that, I'll stop. Happy to take questions, comments.
Great. Thank you, Sham. We have one question in the chat, and others can think about their questions to ask live or put them in the chat. But even if you let me know in the chat, I have a question that I can call on you just to keep it easy. But
There's one.
Douglas Bell writes, for the diabetes study, did you worry about the timing of the complications coming after the medication starts, e.g., that amputation came after the med and not before? And I know we did, but I'll let you answer that, Sham.
Yes, that's a great question, Doug. And we set up all these queries to be temporal in nature, so that all these complications and adverse effects that we looked at come after the start of the medication. And I think for each one of them, we picked a reasonable time period after which they need to appear, so that it does, so that we are confident that it's probably a result of the medication and was not something concomitant for the patient. So this was driven to some extent. So one of the members of our team, she's a pharmacoepidemiologist and a statistician, so she's great in helping out with these, with coming up with that. This is second question from David, were all the rare side effects that were excluded relatively unimportant, or were any of them catastrophic or even deadly? There was one, I would say, which is very rare, but is pretty catastrophic, which is Fournier's gangrene in this medication. And I think in the manuscript, we do include the counts, but we didn't do any statistical analysis because the counts were so small in that. But there was at least one out of the ones which we left out, which I would say was a pretty severe complication. And so one of the interesting things which comes out of doing this kind of pharmacoepidemiological studies with EHR data is at scale is that typically I would guess that catastrophic complications won't happen at a high rate, because if they did happen with the drug, it probably gets pulled off the market pretty quickly. And so you probably end up having medications where these really bad side effects occur at a pretty small rate. And so it does become important that we are able to do the small counts kind of work, and reducing the rounding to ±3 is helpful for that. Yeah, and David, that's a great question. Is that we're also assuming that there isn't a big lag between the side effect and the start of the medication. We're looking for things which happen in a matter of years, months to years, because this particular time period we picked was 10 years worth of data.
No other questions in the chat right now. Those were great ones. Does anybody else have a question they want to ask out loud or anything like that? No? Okay. That's all right. We only have 4 minutes left. I will let you know that our next session is Monday, May 18th at 3 p.m. The likely topic is going to be our clinical concierge evidence service. Still waiting on finalizing some details there, so no promises, but that will be an exciting one. If you're here, you have likely signed up for the newsletter list, so you'll get more information about that. If you have a moment and you wouldn't mind filling out the survey that just popped up, that really helps us get to know what topics or changes in format people would like. So thank you all so much. We'll leave that up there for the next couple minutes. Have a great week. Thank you.